Hi students, welcome to our physics class. This is current electricity part 9. In the previous class, we learned about derivation of expression for equivalent EMF of two cells are connected in parallel and condition for maximum current from series combination of cells and condition for maximum current from the parallel combination of cells. Okay, well, in this class, we are going to discuss about the next very important topic, that is Kirchhoff's law. Well, let's start today's class. Kirchhoff's law. Actually, Ohm's law that can be used to analyze simple circuits, but complex circuits cannot be analyzed by using Ohm's law. Such circuits are analyzed using two basic laws formulated by Kirchhoff. Ohm's law that can be used to analyze very simple circuits, but complex circuits cannot be analyzed by using Ohm's law. Such circuits are analyzed by using Kirchhoff's law. So before understanding these laws, we first define few terms. Those are connected with Kirchhoff's laws. The first one is electrical network. So electrical network, this is the interconnection of circuit elements and energy sources. So this is circuit element. What is this? Resistor. What is the meaning of resistor? Resistor is a circuit element which offers certain opposition to the flow of current. And here cell is the energy source. What is the meaning of cell? Cell is a device which provides the necessary potential difference to maintain the continuous flow of current in the circuit. Okay. The electrical network means that is the interconnection of circuit elements and energy sources. The next very important term is junction. Junction means that is a point. Junction is a point at which two or more than two branches or meet. So here A is a junction, B is a junction, C is a junction. What is the meaning of junction? Junction, that is also called node. Junction or node is a point at which two or more than two branches or meet. Or in other words, junction is a point at which more than two conductors or meet. So the next very important term, that is loop or mesh. Loop or mesh means the closed conducting path. Closed conducting path is called loop or mesh. Any closed conducting path in an electrical network. Any closed conducting path in an electrical network. That is the meaning of loop or mesh. Okay. The next term is branch. Branch means that is a part of electrical network lies in between two junctions. So look at this electrical network, the circuit. So here Actually, A is junction, B is junction, C is the junction. AB is a branch. AC is a branch. BC is a branch. Branch means that is a part. Branch is a part of electrical network lies in between two junctions. Okay, actually Kirchhoff's law that is applicable to both AC circuits as well as DC circuits. It is applicable for both AC and also DC circuits. So Ohm's law that can be used to analyze simple circuits, but complex circuits cannot be analyzed by using Ohm's law. Such circuits are analyzed by using two basic laws that is formulated by Kirchhoff. Okay, so this is the first term connected with Kirchhoff's laws, that is electrical network. Electrical network means that is the interconnection of circuit elements and energy sources. Junction is a point at which two or more branches are meet. Loop or mesh means that is closed conducting path in an electrical network. Branch means that is a part of electrical network lies in between two junctions. Okay, so the next very important topic, that is Kirchhoff's first law or current law or junction law. So actually the statement is very simple. In an electrical network, the algebraic sum of currents in an electrical network, the algebraic sum of currents at junction is equal to 0. So this is the mathematical expression for Kirchhoff's first law or current law, and this is also called junction law. So the statement is very simple. In an electrical network, the algebraic sum of currents at a junction is equal to 0, or simply the sum of currents entering the junction is equal to the sum of currents leaving the junction. Actually, before applying Kirchhoff's first law, we should apply the sign convention. Suppose the currents entering the junction. Look at this, a part of electrical network. Actually, this is a junction. This is a junction. So let us consider that is A. So let us apply Kirchhoff's current law at at junction A. Apply Kirchhoff's current law at junction A. So suppose the currents entering the junction taken as positive. The currents leaving the junction must be taken as negative. This is actually the sign convention. Suppose the current entering the junction, that is taken as negative. The currents leaving the junction must be taken as positive. Okay. So if the currents entering the junction taken as positive, it means here I1 is entering the junction, it is taken as positive. Okay. So plus I1 and I6 is entering the junction, plus I6. I5 is entering the junction, that is also taken as positive. But I2, that is living from the junction A. So I2, that is taken as negative, and even I3 also taken as negative because I3 is also living from the junction A. I4 is also living from the junction A, that is also taken as negative. Minus I4 is equal to 0. So this equation can also be written in the form of I1 plus I6 plus I5 is equal to I2 plus I3 plus I4. Okay, so that means the sum of currents entering the junction, that is equal to the sum of currents leaving the junction. And this law is based on, so what is the significance of Kirchhoff's first law, current law, or junction law? Significance is most important. The significance of Kirchhoff's first law, that is the law of conservation of law of conservation of electric charge. Law of conservation of charge means charge can neither be created nor be destroyed, right? So this is the basis of Kirchhoff's first law or current law or voltage law. The statement is very simple. Algebraic sum of currents at a junction. This is algebraic sum of currents at a junction is equal to 0. Or in other words, the sum of currents entering the junction, sum of currents entering the junction is equal to sum of currents, sum of currents leaving from the junction. Okay. The next one is Kirchhoff's second law or loop rule or voltage law. So this one is very important. So first, listen to me the statement statement of Kirchhoff's second law. Actually, two different statements are there. The first one is in a mesh of an electrical network, the algebraic sum of voltages in a mesh that is equal to 0. In a mesh of an electrical network, in a mesh of an electrical network, algebraic sum of voltages is equal to 0. The algebraic sum of voltages in a loop or mesh is equal to 0. Algebraic sum of voltages in a loop or mesh is equal to 0. So this is the given electrical network. Let us consider this one as A, B, C. So we have A, B, C, A. So this is a closed conducting path in an electrical network. So A, B, TA, that is actually a loop, or that is also called a mesh, loop or mesh. So AB is a branch, BC is a branch, TA, that is a branch. So according to this law, algebraic sum of voltages in a loop or mesh, that is exactly equal to 0. So one more statement is also there. That is, in a mesh of an electrical network, the algebraic sum of product of current and resistance in different parts of the mesh, that is exactly equal to algebraic sum of EMF in that mesh. So this one is very, very important in a mesh of an electrical network. So this is a statement, another statement of Kirchhoff's voltage law or second law or loop rule. What is that? In a mesh of an electrical network, algebraic sum of product of current and resistance in different parts of the mesh, that is exactly equal to algebraic sum of EMF in that mesh. Okay, first here let us consider this one EMF E1, this is EMF E2, and this is resistance R1, and this one is considered R2, and this is R3. Okay, so this is the direction of current, and this branch DC. So this is the direction of current in the branch TA, and this is the direction of current in the branch DA. So to apply Kirchhoff's second law, the direction of currents in a loop is marked. First, we have to mark the direction of currents in each branch of the loop. Okay, current is always drawn from the positive terminal of the cell. So, in the branch CA, is the direction of current is always drawn from positive terminal. Let's consider this one as I1, and the current drawn from E2, that is actually in anti-clockwise direction. Here I1 is clockwise direction, and even EMF is also clockwise. If the current drawn from the cell is clockwise, EMF should be considered as clockwise EMF. Suppose if the current drawn from the cell is anti-clockwise, EMF should be considered as anti-clockwise. So this is clockwise EMF, this one is anti-clockwise EMF. This is clockwise current, and this one is anti-clockwise current. So this is I2, and this one is I3. So I3, that is in I3, that is in clockwise direction. Okay. Actually, here is also cell mistake. This is positive terminal. This one is negative terminal, and this cell having EMF is E3. The current is always drawn from positive terminal of the cell. Okay. So first here we have to choose an indication inside the loop. This point is very important. So here the indication inside the loop A, B, C, A, that is clockwise. So if the indication is clockwise, then clockwise current, clockwise EMF, clockwise current, clockwise EMF are taken as positive, and anti-clockwise currents, anti-clockwise EMF are taken as negative. Suppose the indication inside the loop that is anti-clockwise, anti-clockwise. In that case, anti-clockwise currents EMFs are taken as positive, clockwise currents EMFs taken as negative. But here the indication is clockwise, indication inside the loop that is clockwise. So that is why clockwise currents and clockwise EMFs. Here clockwise currents are I1 and I3, clockwise EMFs are E1 and E3. Is it right? Actually, that is taken as positive because the indication is clockwise. So anti-clockwise currents, anti-clockwise EMFs are taken as negative. So that is the sign convention. Okay. Now let us apply the Kirchhoff's voltage law. Apply the Kirchhoff's voltage law to the loop. What is that? A, B, C, A. A, B, C, A. Apply Kirchhoff's voltage law. Loop A, B, C, A. What is the statement? In a mesh of an electrical network, in a mesh of an electrical network, algebraic sum of product of current and resistance in different branch of the circuit, that is exactly equal to algebraic sum of EMF in the mesh. Okay, algebraic sum of product of current and resistance in different parts of the mesh. So here the first branch is AB. AB. So here actually the indication is clockwise, current flowing in the branch BA, that is anti-clockwise. So the product of current and resistance in the branch BA, that is I2, I2, R2. So this is taken as positive? No, that is taken as negative. Why? Because the indication is clockwise, current flowing is anti-clockwise. So the product of current resistance should be taken as negative. So in the next branch, B2, C, current is I3, resistance is R3, indication is clockwise, current flowing is also clockwise. So the product of current resistance taken as positive. That is plus I3 plus I3 or 3. Okay. In the next branch, PA. Indication is clockwise, current flowing is clockwise, so the product of current resistance taken as positive is plus. Plus I plus I1 or 1. Okay, so that is exactly equal to algebraic sum of EMFs. Okay, in the first branch AB, indication is clockwise. So here current drawn from the cell is anti-clockwise. So this is anti-clockwise EMF. Anti-clockwise EMF means that is negative. So minus E2. So here this is clockwise EMF. So this one is positive. E3 is positive. And this is clockwise EMF. That is why E1 is positive. Plus E1. Okay. Suppose the indication is anti-clockwise. So this sign becomes positive. So this sign becomes negative. This one becomes negative. This one becomes positive. This one becomes negative. This one becomes negative. Right? So the application is very, very important. So this law is based on law of law of conservation. Law of conservation of energy. Law of conservation of energy. Okay, so this is Kirchhoff's second law. So what is the statement? In a mesh of an electrical network, algebraic sum of voltages is equal to 0. Algebraic sum of voltages in a loop or mesh is equal to 0. Or in a mesh of an electrical network, algebraic sum of product of current and resistance in different parts of the mesh, that is exactly equal to algebraic sum of EMF in that mesh. This is based on law of conservation of energy. So this is another example. Now look at this circuit. First here, let us consider this point as A, this point as B, this point as C, D, E, and this one. Yeah. Okay. So this cell having EMF E1, this cell EMF is E2, and one having resistance R1. This resistor having resistance is R2. This resistor having resistance is R3. The current is always drawn from the positive terminal of the cell. The current drawn from the cell 1 is I1. Current drawn from the second cell, that is EMF E2. The current is I2. So here at this junction C, I1 is entering, I2 is entering the junction C. This must be the living current. Let's consider this one as I3. So according to Kirchhoff's first law, what is the value of I3? The sum of currents entering the junction is equal to sum of currents leaving the junction. I3 is leaving the junction, I1 is entering the junction C, I2 is entering the junction. So the sum of currents leaving the junction, that is equal to the sum of currents entering. Means I3 is exactly equal to I1 plus I. Okay. So to apply Kirchhoff's voltage law, the direction of currents in a loop is marked. It is very important. So, and this is the indication in this loop. Let us consider this is loop number 2. This is loop number 1. Okay. So in loop 1, indication is clockwise. Even in loop 2, indication is clockwise. That means clockwise currents, EMFs, are taken as positive. So here is also the clockwise currents or EMFs are taken as positive. So anti-clockwise, that is taken as negative. Okay. This is the second example. So here apply Kirchhoff's voltage law to the loop. The loop, that is A, B, C, F, A. A, B, C, F, A. This is a closed conducting path of an electrical network. So from A to B, what is the value of current? I, resistance R1. Current is I1, resistance is R1. Indication is clockwise, current flowing direction is also clockwise. That means the product of current resistance taken as positive, right? Plus I1 R1. Okay. In the next branch, the indication is clockwise, current flowing is anti-clockwise. So from B to C, there is no resistance. Okay. From C to F, the resistance is R2, current is I2. So the indication is clockwise, current flowing is anti-clockwise, means the product of current resistance should be taken as negative, minus I2 or 2. So that is equal to, so here E1 is clockwise EMF, that is positive. E2 is anti-clockwise EMF, that is negative. So the algebraic sum of product of current and resistance in different parts of the mesh is equal to algebraic sum of EMF in that mesh. Okay. After that, again apply Kirchhoff's voltage law to the loop. The loop, that is C, D, C, D, E, F, C. Okay. C to D, there is no resistance. D to E. So what is the value of resistance? R3, current is I3. So this is a sign here, that is positive. Why? Because the indication is clockwise, current flowing through R3, that is also clockwise. So plus I3 R3, that is next branch A to F. Here there is no resistance. Next F to C. The resistance is R2, current is I2. Indication is clockwise, current flowing is also clockwise. So the product of current resistance I2 R2, that is taken as positive. Okay. And that is exactly equal to, so E2 is clockwise EMF, that is taken as positive. Okay. So after that, what is the value of I3? I3 is I1 plus I2 into R3 plus I2 R2 is equal to E2. Okay. So this is very, very important. Thank you.